In this video, I'd like to introduce these operators and the algebra operator. This is a little preliminary toward to the theory, linear theory of a second and third order linear differential equations. To understand this operator algebra, we need to review about functional notation. First, let me explain a function in this way. Here it's a bag of numbers. It's my favorite way of explaining these things. So not number line anything, it's a bag of numbers. And here's the same bag of duplicate of numbers. What the function does is that you choose a number and going through this machine, and this function changes number to something else here. So that process usually given by an expression, algebraic or transcendental expression you have learned in your education, but abstractly I'd like to introduce it as an instruction on algorithm. I give you a number and I can give you a very specific instruction to what to do with that number. And as long as you understand the algorithm and you understand that algorithm is applicable for any numbers I pick from this bag, you understood the function, and the existence of a function is explained in this way. And function exists as long as you understood the instruction or the algorithm that is given. Often these are given by an algebraic expression, but it doesn't have to be. So algebraic example is like this. If I give you a number x, whatever that is, we're going to square that and add it to the original number, and finally you add 1. So if you do that with given number 1, and it's going to change that number to 3. So that's one description of a function. Given a number, you go through this instruction or algorithm. If it is not algebraic like this, like some playful things we can do about the number, that also makes a function as well, as long as the instruction and algorithm is concrete and specific. The main purpose of this video is actually introducing this notation. So notation, let me hide this bottom part. Notation f versus f of x. F of x is a number. If I give you a number, arbitrary number x, if you do this instruction or algorithm or this expression, the output, which is also a number, is denoted like this. So technically speaking, this f of x is actually a number, given x is a number. First is this notation f. F stands for this entire idea. Maybe idea or the instruction, algorithm is a good word. No one will say an instruction is a number or an algorithm is a number. So that f stands for this entire idea, while this f of x stands for a particular number. Given x, this will represent a number. What you need to get used to is this representing this entire instruction algorithm by one letter and distinguishing it from this output, which is a number. Suppose you're given two functions, two algorithms like this, f and g. So I want you to think about the meaning of f plus g, one idea, one instruction, and another instruction, and f plus g, the sum of these two instructions, versus f of x, which is a number, g of x, which is another number, and adding these two things. There is no question about the second part. We know the meaning of a sum of two numbers. But this one is a little strange. I have one idea, f is given by this idea, g is another instruction or algorithm or idea. And what does it mean, f plus g? It really means this, but that's the new name for our new idea. What this algorithm instruction is, given a number x, and here, we're going to go through this algorithm f, and another algorithm that is also specified earlier in this context, and then we're going to add these two output, and that'll give us a new result, new output. So that function is named by this f plus g. So again, you have to distinguish these two notation. These are the sum of two numbers. Is this new notation of a new idea out of given two ideas.